Yeah. Thank you, everyone. Thank you for joining in time. And let's. So this is the only slide that I have, and I was seriously not joking. Okay. So this is the only slide that I have for today. Rest all is going to be hands-on. Will that be okay with everyone, or do you want to go in the presentation mode normally, as things are conducted? So what's the audience outlook? Okay, do you want to have a PPT based learning, or do you want to have the practical learning? I called it as practical hypothesis testing, right? For that very reason, I intentionally avoided all the PowerPoint presentations. Okay, so this is the only slide that I have, and let's directly move on to the practicals. Okay, so of course there are some prerequisites. Okay, I expect people are decently comfortable with statistics, mean, mode, median, standard deviation, definitions, variance. Okay, because this is, I mean, we have very less time to cover all of these things. Okay, so I am assuming some prerequisites, frankly, also including Python coding. Some programming basics is very clear to everyone. Okay, although we won't be doing any sort of exotic functions and loops, and those things are not needed, but at least single liner computations, calculations using NumPy, that should be okay. I'll anyway share the codes at the end of the session with everyone, right? And coming back to the statistics. So as I said, I'll be assuming some basic descriptive statistics familiarity with the entire audience. Mean, mode, median, standard deviation, variance, and all, population sample. And what else? From the probability side, basic probability definitions, probability distributions. What is a probability distribution? And the two types of probability distributions. So if you want, I can have a quick refresher on that. Okay, but not more than 5 to 10 minutes. Okay, and we have to start with the actual content, and the actual content will start with the normal distribution, properties of the normal distribution. We'll also look into the central limit theorem and how can we utilize the central limit theorem for hypothesis testing. Okay, because the entire basis of hypothesis testing, okay, the framework, the background lies with the central limit theorem, at least most of it. Okay, if not all. And I'll be taking different types of tests, what test to use in what kind of scenario. Okay, and for each test I have a business problem. Okay, and then finally I'll also be concluding with confidence interval calculations. Okay, that would be the end part of this session, and I'll take one example of the chi-square test also. So this is the whole plan. So let's get started immediately. Share the code, or we can write. No, we would not have, Kareem, enough time for everyone to write down the codes. Okay, but I would definitely need your inputs, because the hypothesis, the null and the alternate hypotheses is what I would be asking from the audience. Okay, depending on the understanding of the business problem. So for each of the problem statements, I would want you to formulate the hypothesis, and then once the hypothesis is formulated, we will implement it, or rather I will implement it and show it to you. Okay, or if you actually want to do it, maybe I can pause there, you can write down a code and give me the output value at least. Okay, so I can verify the output value. Even that is perfectly fine. I get one request here. Explain type 1 and type 2. We will be talking about type 1 and type 2 errors, but with respect to hypothesis testing and not confusion matrix. There is a lot of confusion within the confusion matrix, and which is why it is called as confusion matrix, pun intended. So maybe sometimes I can take another session on confusion matrix, precision, recall, calculations, and what metric to use in what kind of scenario. So just request those guys. I'll be up for another session. Okay, but here let's narrow down, because the topic itself is having too much of a breadth and depth involved. Will need some time. So I may not strictly finish in 1 hour, frankly. Okay, so maybe 10-15 minutes over. I hope that is fine with everyone. Okay, so I'll start from the very start. Don't worry. Okay, I'll not assume anything about hypothesis testing, but just now said I'll assume some familiarity with statistics, probability, and definitely Python. So that is a prerequisite. Okay, perfect. So this slide is done. And what is next? So I actually have a couple of slides but okay, let me just pull that up. Okay, so I'll start with this. Okay, so it's a real it's a real occurrence. Okay, this is not made up scenario here. Okay, absolutely a real occurrence. Okay, so I'll come to the definition. Let's have a look at this. So what happened on 9th of November 1965 is that there was a power failure in the city of New York, and that resulted in a sort of a blackout for almost 12 hours. Okay, and the surrounding areas. 9 months later, it was found that in the August 1966, who found? The New York Times, actually. They are the people who found, and not just found, they published a series of 3 articles claiming that the birth rates in August 1966 was higher than the normal based on the interviews with the city doctors and all. So they called these babies as blackout babies. So what they were indirectly trying to claim is people didn't have anything else to do than merrymaking in those 12 hours. And the result is increased birth rate exactly 9 months later. So everyone might be amused now, right? Yeah. So the articles published by the New York Times raised a very interesting question. Okay, whether the power failures actually resulted in this additional birth rate or procreation. So 15 years down the line, these 2 guys who are actually statisticians, okay, they use some time series analysis data and claimed finally that there is not enough evidence to suggest that this 1965 power failure resulted in the increased birth rate 9 months later after the blackout. So what is the moral of the story here? The guys who are reporters, whatever the numbers you see on your TV channels, until and unless it has been validated by a team of statisticians, they tend to jump into conclusions very fast. So that is a big problem. Okay, if you get 2 numbers, looking at those 2 numbers, you will get some intuitions. Whatever intuitions you have in your mind might just be bluff unintentionally. Okay, I'm not saying that New York Times published that article deliberately, but it could be just a misguided article altogether. And that was proven by these 2 statisticians because they studied real data, not just interviews, not just doctor interviews. They pulled out the entire record book, okay, of each and every hospital within the New York City and the surrounding areas. And actually with data, they had proved that there is not enough statistical evidence to say that this additional birth that has happened, okay, is actually due to that power failure. Yes. So basically then what are we trying to do in hypothesis testing? Okay, so we are either, so there is a claim, usually there is a claim. So someone has to make a claim first. I can make a claim, you can make a claim, the company can make a claim, the community can make a claim, those reporters can make a claim, anyone can make a claim. Okay, so anyone who is making a claim, until and unless that claim is against the norm. Normally the claim has to be made against the norm. The claim should not be obvious. So if I claim the sun rises in the east and sets in the west, do you need any hypothesis testing for this? It's not even a hypothesis. It's the truth. It's the, truth, the ground reality. It's not a hypothesis anymore. So you don't need any proof. I mean, all billions of years, the same thing has been happening. So this statement that the sun rises in the east and sets in the west, if I say that this is my claim one fine day, this is not a hypothesis at all. Okay. So typically people would be interested in your hypothesis or your claim when it goes against the norm or when it is something interesting. Okay. I'll give you a couple of more examples. Okay. So actual business cases now. Okay. Can I increase the size slightly? Yes. Okay. I'm sure this is visible. Okay. So now these are several claims made by, various companies. So one claim is made by Complan. People in India very well know about this company owned by Heinz India. They say that they claim that children who drink this health drink called as Complan, they are likely to grow taller compared to their peers. Okay, another company called as Horlicks, they are claiming that not just taller, stronger and sharper as well. So 3-in-1 kind of health drink they are claiming. Okay. Cream, everyone knows about these two creams in India, very popular. Okay, Fair and Lovely and Fair and Handsome. Fair and Lovely is a HUL product. Fair and Handsome is a Imami product. Okay, so two different companies are making very similar names, and both are claiming that they can make you fair and lovely or fair and handsome. Actually, Axe, everyone knows about it. Axe effect. There is another claim that women tend to use more camera phone more than men. I mean, okay. Beautiful people are likely to have a girl child. Also, this is one of my favorite. I also have a daughter. So definitely I'm good looking. Okay. Married people are happier than singles, and so on and so on. Okay. Vegetarian tends to miss few slides. Smokers are better salespeople. You can keep on going. Okay. So these are some example hypotheses or claims. Okay. Some of these claims are made by media houses. Some of these are made by your companies. Individual claims could be there, biases and everything, right? Fine. Any questions still here? Any questions? Okay. So before I start defining how to, not just define, how to actually create a hypothesis test in the first place, let's go back to the prerequisites. Okay. So there is only one slide here, which I would like to come back on this. So hypothesis testing is a process to either accept or reject a null hypothesis. What is a null hypothesis? Let me define that. So you claimed that the average salary of the MBA graduates coming from marketing specialization is higher than the MBA graduates who are than the average salary offered to the MBA graduates from HR and admin specialization. So let's say the dean of a B school, a business school, dean is claiming that the average salary offered, okay, during placement to the MBA graduates coming from the marketing specialization is higher than the average salary offered during campus placement compared to other branch, let's say, or other stream, let's say HR and admin. So that is the claim made by the dean of that business school. How do I nullify that claim? So the entire process of hypothesis testing is to validate that null hypothesis. So what is the null hypothesis? Null hypothesis is the hypothesis which invalidates the claim made by someone else. So right now, the dean of this B school is making the claim. I want to invalidate that person's claim. Okay. So the process of validating or invalidating the null hypothesis, that is called as hypothesis testing. So the whole intention of this entire exercise is to validate or invalidate the null hypothesis, not your hypothesis. Okay, what is the null hypothesis? The hypothesis which will be created to invalidate your claim. So if that dean is claiming that the average salary of MBA graduates from marketing specialization is higher, then the null hypothesis would be it is less than or equal to the other branch, the other specialization. It is as simple as that. So you have to talk about two things. One is the population parameter here. What population parameter we are talking about? We are talking about the means, and mean being less than something, more than something, equal to something. So the entire claim is made about these. Okay. So in today's session, I'll only focus on the claims made about the population mean. Okay. Once again, I repeat, in the parametric tests, okay, I'll only focus on those claims which are related to population means. You can also make claims about the population variance or population proportions. Okay, so you can get all the other types of hypothesis test in any standard statistics textbooks. Okay, okay, so we have to narrow down somewhere. Okay, fine, perfect. So now I have some notes here. These are my handwritten notes. I'll share a PDF with you if you want. Okay. So I'll directly start with the normal distribution. Okay. I'm assuming a decent familiarity of probability distributions here. What is entire population is the entire database. See, the data that you have in hand can be considered as the sample, because you cannot really get the entire population's view. I mean, so whatever data you have gathered is always the sample. Okay. So literally, whatever, calculations you will be doing most of the times will be assuming that that particular data set is your sample, until that data set is huge. Let's say the data set is having billions of data points or millions of data points. Then that data set is very close enough to what the population is. Okay, then there would be hardly any difference whether you consider it as a sample or you consider it as a population. That will not make much of a difference. Ashwini, your question. Okay, so that was the question I was answering. So please post all of your technical questions in the Q&A section only. I'll be only watching the Q&A section, not the webinar chat. Okay, fine. PDF you will get. Okay, don't worry. So I did not get time to make PPTs. So I mean, I'm not a PPT guy, as just now I told you. So these are my handwriting. I mean, I hope this is, legible. Okay, good. So I'm assuming that everyone is slightly familiar with a probability distribution. Okay, yes or no? So see, there are two types of probability distribution depending on two types of variables. So we have two types of variables. One is discrete random variable and one is continuous random variable. Discrete random variable you understand by categorical variable, again, which is nominal or ordinal. We'll not get into that breakup because that breakup doesn't matter in hypothesis testing. So there are two types of variables in any data set. Everyone knows this, right? So discrete variables and continuous variables. So continuous variables will follow some distribution and discrete variables will follow some another distribution. Okay. So we are going to talk about properties of these kind of distributions. Okay. So some of these properties of these distributions we are going to talk about. If you want, I can summarize those properties like CDF, that is your cumulative distribution function, or PDF, okay, or PMF. Is everyone aware of these terms? Okay, perfect, perfect. That's a huge time saver, actually. Okay, that's a huge time saver. Just in case, if you know these things, then I really don't have to get into all that, and we can directly get started with the actual content. Okay, perfect. Okay, so there are some questions coming up. Can you please explain null hypothesis? I'll explain you everything. Okay, don't worry. I have proper case studies. So unless we talk about a particular case study, okay, uh, framing the null hypothesis or giving an actual example will not make sense. Okay, so don't worry. I'll actually give examples of each of them. Fine. So that is done. That is done. And this is also done. Fine. So Ashwini is saying the natural opinion is the null hypothesis. Maybe, may not be. Okay, let's not generalize. Let's not generalize. So until we get to the section where we are defining the null and the alternate hypothesis, we'll not talk about the hypothesis. There are a lot of prerequisites which come before hypothesis generation and testing. Okay, so let me quickly cover that in another, let's say 10 minutes, 15 minutes. Okay, so normal distribution, everyone knows, it's a pretty symmetric distribution. It's a 2-parameter distribution. So we have to know the mean value and the standard deviation. So any normal distribution will be characterized by these 2 parameters. Okay, mu refers to the mean of the distribution. Sigma is the standard deviation of the distribution, correct? It is a 2-parameter distribution. So it is symmetric. What does that mean? So area under the curve from negative infinity till the mean is equal to the area under the curve from mean towards the positive infinity. So it's symmetric. So half area is before the mean, half area is covered under the curve after the mean. Okay, so that is the second point here. Area under the curve on both sides is equal. That is why I'm calling it to be symmetric, and they are same, and 0.5 and 0.5. That is what. So we will not get into all that expressions. But what did I do here? I'm integrating P of x dx. What is P of x? That is a probability distribution function. X is my random variable. So I am integrating the probabilities from negative infinity to the mean. So what does that mean? That means that I'm summing up all the probabilities that this random variate can take. Okay, what is the probability that a random variable x can take a value between minus infinity and mu? That is given by this left side. And what is this? This is the sum of all the probabilities, that summation becomes integral for a continuous distribution. Okay, so for a continuous curve, the summation becomes integral. So it is actually the sum of all the probabilities that this random variable x can take from mu towards positive infinity. So any value from mean towards positive infinity, all those probability values are added, and that cumulatively is equal to 0.5. Okay, and another very important property is, since it is symmetric, so the mean, median, and the mode value of the normal distribution are all equal. What is mean? Normal average. What is median? Median is the center point of the distribution. So when you arrange or sort all the values in an increasing order or decreasing order, okay, the middle point of the distribution is called as the median, right? What is mode? The most frequent value of the distribution is called as the mode value. Fine. So I've given some calculations. You can check that. This is the most important point. Okay, you can see this graph from the Wikipedia page of the normal distribution also. Like, so within one standard deviation, so mu is the peak minus sigma plus sigma. So within one standard deviation of the mean, you have roughly 68% data points. Within 2 standard deviation of the mean, you have roughly 95% of the data points. And within 3 standard deviation, we are covering almost 99.7% of the data points. So these are all the standard properties of a normal distribution. Okay. Coming to the definition of population and sample. So population is the complete set on which you can draw several samples. Okay. Now, whether you are drawing samples, different sampling techniques are there: bootstrap sampling, stochastic sampling, random sampling. So I'll not get into the sampling techniques, but there are several sampling techniques you can easily get from any statistics books. Okay, so population is the complete data set that you have in hand, let's say, and sample is one part of or one subset of that data set. That is your sample. Now the mu, sigma, and sigma square. Mu is the mean, sigma is the standard deviation. How do you define standard deviation? Standard deviation would be like mean, okay, or the variance is your sigma square. So sigma square or the variance can be defined as the mean square deviations of the data point from their mean values. Mean square deviation from the mean values is your variance. So standard deviation becomes root mean square deviation of the data points from their respective mean values is your standard deviation, right? So some basic things I'm assuming. That's the reason I'm not spending enough time in explaining all that. And I'm actually going a bit fast. I know this. Okay, so these are called as population parameters. So this is one very, very important point. Okay, so we are going to refer to them as population parameters. Perfect. The corresponding values for a sample. Okay, so what is X bar? X bar is my sample mean. What is this S? This S is my sample standard deviation, and the small s square is the variance of the sample. Okay, same, the corresponding values for a sample. But these corresponding values for the sample are not called as parameters. They are called as characteristics. So each sample from the same population will have different characteristics. Okay. So let's say you are drawing 4 samples from the same population. So each of the 4 samples here are going to have their own characteristics. That doesn't change the population parameters. So population parameters are going to be constant, but depending on how you have sampled it and what is the size of the sample characteristics will keep changing. I hope that is clear, right? Fine. Then it is clear. So this is the formula typically you would be using for standard deviation, and this is the variance. So you can see xi is my ith value of the variable, mu is the mean. So xi minus mu becomes the deviation. You are taking the square of the deviation, and then you are taking the sum of the squares of the deviation and then dividing by n. So that is, what does that become? Mean square deviation of the data points from their mean values. So deviation from the mean values. So mean square deviation of the data points from their mean values. That is how you define your variance. Okay, so the biggest difference between the formula between standard deviation and the biggest difference between the standard deviation formula for population and sample is this, what I have already highlighted. Can you see that 1 over n minus 1? In the case of a population, this will be n, correct? There is a n over here and there is a n minus 1 over here, where n in this case is being referred as the sample size. Okay, that is your sample size. Fine. Can I do a annotation? See, is that possible? No. Anyway, so here again the same denominator. Here was n, capital N, that is the total number of data points in the entire population, but here it is again n minus 1. So you are reducing it by 1, and there is a reason for it. Okay, so normally we call it as Bessel correction, and we can also interpret it by the degrees of freedom. So what is that degrees of freedom? Basically, while calculating the standard deviation and the variance, you are using one of the sample parameters, or you can see that X bar is being used to calculate the standard deviation and the variance. So you are using one of the parameters from the same sample, and so the degree of freedom will decrease by 1. Okay, and so the degree of freedom will decrease by 1. So we'll call it as DDOF. Basically, that is the difference between n and the degree of freedom. So basically, the degree of freedom is n minus k. Why do we need to bother about this? Will come in the t-test. So I'll come back and revisit this point. Okay, so finally, let's come to the interpretation of the curves once again. So the area between A and B is interpreted as the sum of probabilities of all the values that this data, this variable x, can take between A and B. That is how you can interpret about the area between A and B, right? So this is how we write down mathematically. Fine. So how do you define the cumulative distribution function then? Okay, so what does CDF represent? CDF represents the probability that a random variable x can take a value which is less than or equal to some value A. Okay, so how do I define that? So you can see it here. So P of x less than or equal to A, mathematically we can represent it this way, minus infinity to A. So that is basically integration from minus infinity till that A. This yellow highlighted position area, this yellow highlighted area, that is called as your CDF. So that is a cumulative probability that your random variable x can take, okay, a value which is less than or equal to a, less than or equal to a from minus infinity till that point. Okay. Conversely, the area on the other side, the remaining area, which is 1 minus CDF, okay, is referred as survival function. Can you see this green area? So the area from the right side is called a survival function. The area from the left side is called CDF. The reason I am explaining these things is exactly I'll be using the same functions for my hypothesis testing. Okay. So if you want, you can take a quick snapshot of this, not to get confused later. Okay. While I'll be doing the actual practical examples. Okay. I'll be actually using the CDF and the survival functions available within SciPy module. So we have the functions readily available. We don't have to do all that integration from scratch, but a thorough understanding of the CDF and SF will be needed. Okay. So CDF plus SF becomes your total area under the curve, which is equal to 1. Why is it equal to 1? Because the total cumulative probability that this random variable can take any value from minus infinity to plus infinity will be 1. Array, you are 100% sure, no, that this X will take some value from minus infinity to plus infinity? You are 100% sure. That is why the total area has to be equal to 1. So 1 minus CDF is your survival function, right? So survival function is area on the right side. CDF is the area on the left side. It is as simple as that. Perfect. Okay. So you can also actually find out. So let's say you are given the area and you want to find out until what point that area would be covered. So this time I have the value of the area. I want to find out what is the value of A until that area would be covered. Or similarly, let's say you have an area from the right side. That cumulative area is something. You want to find out the point B until which that area would be covered. Let's say I want to find out from the right side how much area, until what point area of 0.05 would be covered. Area of 0.05, that is the cumulative probability of 0.05 would be covered from the right side. I want to find out that point B. So to find out that, you will have to take the inverse of the survival function, because it is the area on the right side. That is what we call as ISF. And if you are talking about the area from the left side, then you take the inverse of the CDF function, which is what we call as PPF. So PPF is the inverse of that area function from the left side, and ISF is the inverse of the area function on the right side. So 4 functions, and the 5th function is your PDF anyway. So I'm not going to use PDF at all. That's not needed in hypothesis testing. But these 4 functions are the core of entire hypothesis testing. Okay. So each and every exercise, each and every example is going to use only and only these 4 functions. Whether it is a Z test, T test, chi-square test, everywhere I'm going to use only these 4 functions. Fine. Okay. But what is the standard normal distribution? So can I standardize my distribution? So a standard normal distribution will have a mean exactly equal to 0 and standard deviation equal to 1. So you can have any number of normal distributions, but until and unless the mean is 0, so you can see the red curve is having a mean equal to 0. Okay. And standard deviation is equal to 1. So when the standard deviation is smaller than 1, it becomes a narrower distribution, as you see here. Okay. And when the red one is a narrower distribution. This blue one is a standard normal distribution because the sigma is 1, and the black is a flatter distribution. Can you see? So that is a broader distribution. So a broad distribution will have standard deviation greater than 1. A narrow distribution will have a standard deviation less than 1. And normal distribution, that is a standard normal distribution, will have standard deviation equal to 1. So these are the properties of the normal distribution, which I have originally discussed. So this is very clear. If sigma increases, distribution will become flatter. Sigma decreases, distribution will become narrower. Perfect. You can always standardize it. So anyone remembers the standard scalar function in scikit-learn? Any of you? Standard scalar? Right. So what does that standard scalar function do? So that standardizes any variable. So that will subtract the mean. So that will convert into the Z score, right? So this minus mu was supposed to be here. So, oh, sorry, minus mu. So yeah, this is the formula. So this is the formula. You are subtracting the mean and dividing by the standard deviation. That is basically you are standardizing that variable. Correct. So you are removing the mean and scaling it to one unit variance. Okay. So let's say you have the age of all the passengers who were traveling in that Titanic ship. So the minimum age is 0.42 years. The maximum age is 80 years. The average age is close to 30 years. When you standardize it, you will get a similar curve. The shape of the distribution does not change. Please understand this. You are not changing the shape of the distribution. You're only changing the scale of the distribution. Now the peak is at 0. Earlier the peak was at 30, but now the peak is at 0. What was the original standard deviation? Some number. Now the standard deviation is exactly equal to 1. So that is what I'm calling it as standard normal distribution. So there are some questions. Some people are asking me to repeat CDF and PDF. I'll repeat that in the hypothesis testing now. Okay. That is where the actual application is. Fine. So let's take a quick exercise. The first exercise, with this much amount of knowledge, can I actually solve a business problem? This is not a hypothesis testing problem, but still a business problem, which can be solved by purely the knowledge of normal distribution. So this is how the question goes. According to a survey of smartphone users in India, these are made up numbers, so don't worry. The smartphone users spend 68 minutes in a day on an average in sending messages, and the corresponding standard deviation is 12 minutes. Now assume that the time spent in sending messages follows a normal distribution. What proportion of the smartphone users are spending more than 90 minutes per day? Second, what proportion of the customers are spending 20 minutes, less than 20 minutes, sorry. And third, what is the proportion of the customers spending between 50 to 100 minutes? So these are the three questions I want to solve using Python code. Ready? Ready? So I'm going to solve this question using Python code, but we need to understand what we are trying to do first. Okay. So you have to convert your business problem into a mathematical problem, okay, which can be solved before. So you guys can take some time, understand this, try to come up with a mathematical version of the solution. So basically, when I say mathematical version of the solution, what probability are you looking for? Okay. So do something. In the meantime, let me answer. There are 10 questions in the Q&A section. Let me take each one of them one by one. So there is one question by Ernani. Why sometimes I see n-1 instead of n? That is the case when you are talking about standard deviation or variance of a sample. For a for a population, you would always see divided by n only. And yeah, so that is answered. So please do not send hi messages on the Q&A section. Okay. Ayush is also asking the similar question. Why we take n-1 in the denominator? I just explained, because of the Bessel correction. See, there are two ways you can explain that Bessel correction. One is with respect to the degrees of freedom, and second, okay, maybe I'll just so think about this. Okay. Now the problem here is I cannot annotate on this. Let me see if this works. I hope this works. Yeah, this works. Okay. So now if you are taking a sample, this is how your sample would be, or this is how your sample would be, or this is how your sample would be. Correct? Your sample will never cover everything from this end to this end. So samples standard deviation is always underestimated. Do you guys agree with me? See, population is varying from this end to this end. but the sample is varying from this end to this end. It will have a narrow range. It will always have a narrower range compared to the population. Do you guys agree with me? Yes or no? Quick. The range of variation for the sample will always be narrower, and hence the variation of sample will always be lesser compared to the variation you would actually observe in the population. And now let me convert that statement into technical terms. And hence the variance of the sample is lesser compared to the variance of the population. So the variance is always underestimated. So sample variance is always underestimated. And because of that, I have to increase the overall fraction. And how do you increase the overall fraction? By decreasing the denominator. If you decrease the denominator, the overall variance will increase and get closer to the population. So that is another way you can justify why did you subtract 1? Because by doing that, I'm decreasing the denominator. Okay, and so the overall fraction or the overall quantity increases. So what happens due to that? If the overall quantity increases, that will actually try to reflect the actual variance of the population. That will get closer to the variance of the population, right? So that is another reason for the Bessel correction. I defined it as a Bessel correction. Another is degrees of freedom. You are already extracting one parameter from the sample. So the degrees of freedom has reduced by 1. Okay. So that is another way. So fine. That much should be fine. Okay. So this is also done. Degrees of freedom. What is degrees of freedom? Okay. So someone asked that degrees of freedom is how many parameters you are extracting or calculating from the same sample. So if you are calculating 5 parameters from the same sample, then the degrees of freedom is reduced by 5. It is always n minus k. Degree of freedom is defined by n minus k, where k is the number of parameters which we are calculating from the sample. Okay, so here I calculated one parameter from the sample while finding out the standard deviation. So degree of freedom is reduced by 1. Okay, so now the degree of freedom is n minus 1. Okay, Ashwini is asking how to decide standard normal deviation is better than min max. Okay, that is irrelevant question because that should be taken in a more machine learning scenario, or maybe I can take that in the end. Chinmay is asking 68, 95, 70, 97.7 is only for standard or only normal? Standard normal or only for normal? Yes, it is actually valid for both. Any type of normal distribution, whether it is standardized or not. Okay, as long as it is a proper normal distribution, it will have the same distribution. A skewed normal distribution will have a different fraction. Okay, skewed normal distribution. So as long as your normal distribution is not left skewed or right skewed, the numbers would be the same, whether it is standard or not. Clear? That is clear. Inverse SF and that I'll answer later. And anonymous attendee has asked or commented, we find the expectation of sample variance, then we'll be able to find, yes. Okay, so regular comments on the other side, please. Only questions on this side. Okay, coming back to the point now. I was talking about solving this question in the Python code. So let me open my Python code, and I hope you have understood this problem statement. Okay, if not, you can take a quick screenshot. You have the numbers ready with you. I also have the numbers ready with me. Okay. Okay, I need some space here. Fine. So can I calculate that? Yes, we can calculate that. So the first one was this. Let me slightly zoom out. So what proportion of the smartphone users are spending more than 90 minutes daily? Okay. So you are looking for the proportion of the smartphone users who are spending more than 90 minutes. So essentially, what is you are trying to ask, what is the probability that the random variable X, what is X here? X is the time spent on mobile phone usage. So what is the probability that this random variable X can take a value more than 90? So the answer to your question is this probability, P of X greater than 90. So you are looking for the area under the curve from 90 till positive infinity, everything. How do I get that number? So, okay, from scipy dot stats import norm. So I'm importing my normal distribution. And then norm dot, since it is the area from the right side, I'll have to go for survival function. Okay. 90 towards positive infinity. Here the location of the mean is at 68 and the standard deviation is how much? 12. So this is your answer, 0.033. So 3.3% of the people are spending more than 90 minutes in usage. It is as simple. You see? Back to the next part. Okay. So what proportion of the customers are spending less than 20 minutes? So that brings to me on this side. Okay. Less than 20 means I want to find out the probability that X will have a value less than or equal to 20. So essentially I'm looking for the area under the curve from minus infinity till 20. So from the left side, the area would be, so the same control A, control C. This time I'm looking for the CDF. That is the area under the curve from the left side. Okay. Until what point? 20. And this is your answer. This is your answer. So basically 20 is roughly 4 standard deviations away from the mean. And that is why this probability is very, very small. Once again, I repeat, 20 is 4 standard deviations away from the mean. How do you know that? See, 20 minus 68 divided by 12. What is 20 minus 68? 48. 48 by 12 is 4, correct? So 20 is 4 standard deviations away from the mean. Please understand this, what I said. When you standardize it, that 20 will become minus 4. This 20 will become minus 4. That is the reason standardization was created, okay? So 20 is minus 4. So it is 4 standard deviations lower than the mean. Since it is very far from the mean, the area under the curve would be very, very small. And that is what has happened here. The area under the curve is very, very small. So that is the probability is very, very small. What is the third point? What proportion of the customers are spending between 50 to 100 minutes? So here you are referring to this area now. Okay. So that is the area in between 50 to 100. So how do you get the middle area now? So I have a plan. Let's calculate all the area till 100 and then subtract the area till 50. So automatically you will get the area from 50 to 100. There is no other function. So I'll get all the area from minus infinity to 100, then subtract the area from minus infinity to 50, and then the remaining area will be obtained. That is your answer, C. The probability that this random variable X can take a value between 50 to 100. Correct? So how do I get that? I'll just copy and paste the same thing. This will be 100 and this will be 50. And that's your answer for the third part. Okay. Sorry, instead of SF, you will have to go for CDF because you are finding the area from the left side. And which is why this was coming out negative. So 92.9. So roughly 93% of the people are spending. Roughly 93% of the people are spending time between 50 to 100 minutes. We have got this answer. 92.9. That is the proportion. Multiply by 100, you'll get the percentage easily. So this is the interpretation, and this is how you calculate, use your Python code to solve a real business problem. So you see, there are 3 steps. One is to understand the business problem. Second, to convert that business problem into a mathematical problem. You need to have a mathematical equivalent. Until and unless you are mathematically clear what you want to compute, you will not be able to get into the code part. And code is only executing the mathematics that you have derived from the business problem, right? So the same thing is also going to happen for hypothesis testing. So now before going to the hypothesis testing, one last prerequisite is central limit theorem. Okay. Okay. So what is central limit theorem? Yes, I will give you the notebooks also. Okay. And Ashwin is asking me to explain again. Okay, please go through the. So anyway, just stay in the session because the same thing will get repeated for every other exercise. So automatically it might have synced only 50%. It might have just gone into your head only by 50%. That's okay. But the next exercise it will become 70%. But the next exercise it will become 100%. Okay. So just stay and be patient because I cannot keep repeating the same things. We have a time constraint. It's already 8 o'clock and we have not got into hypothesis testing. So easily I can see another half an hour from this point. Fine. So what is central limit theorem and where do we use that? Okay. So basically there are three assumptions. We have to first understand the assumptions. So there is a whole population and I'm drawing multiple samples. So what are S1, S2, S3? These are different samples drawn from the same population. So now each sample will have a mean that is represented by X bar, X bar, X bar, X1 bar, X2 bar, X3 bar, Xk bar. So K samples, K sample means. And similarly, I'll have S1, S2, this is small S1, S2, S3, Sk. Okay, which are my sample standard deviations. So now if you see the population standard deviation is given in red and different samples will have a sample standard distribution, correct? The population distribution is given in red and different samples I am drawing. So as long as your sampling is done without any bias, okay, as long as you are drawing sampling without bias, okay, as long as the sampling process is really good, the sample distribution will resemble very closely to the population distribution. I'm not calling it as normal distribution. So listen to my words very carefully. As long as your sampling process is very efficient, the sample distribution will resemble very closely to the population distribution. Whatever be the population distribution, it could be Bernoulli, it could be binomial, Poisson, Weibull distribution, binomial distribution, uniform distribution. It doesn't matter. Geometric distribution, exponential distribution. These are several distributions. Doesn't matter. What I'm saying is your sampling has to be efficient enough so that its distribution is very similar to the population distribution. This is one of the major assumptions. Okay, a biased sample will have a distribution significantly different from the population distribution. See, this is how a biased sample will look like. Can you see? This is how a biased sample will look like. So a biased sample will have a distribution significantly different from a population distribution. Okay, so this is how you can immediately figure out my sample is definitely not the right sample to do hypothesis testing. You should discard such a sample for hypothesis testing. You should never take such a sample for hypothesis testing. Okay, so you need to have a sample for hypothesis testing. That is very clear indirectly, correct? And what kind of sample? A sample which is representative of the population. That is the right sample for hypothesis testing. Clear? Okay. And further, there are a couple of more assumptions. One is saying that these are IID samples, independently and identically distributed. That's what I just now explained, that each of these samples that I'm drawing has a distribution which is very similar to each other and also similar to the original population distribution. Fine. And they have been drawn independent of each other. So that is why we call it as bootstrap sampling or sampling with replacement. So suppose you have 10,000 data points and you are drawing the first sample of 2,000. Now the second sample will not be drawn from the remaining 8,000. That will again be drawn from the entire pool of 10,000. The third sample will not be drawn from the remaining population. No, it will again be drawn from the remaining from the original overall population pool. Okay, so that is what I meant by saying independent sample. So if there is a data point which entered into the first sample, it has equal probability to enter into the second sample and the third sample as well. or if there is a data point which did not make it to the first sample, it is having the same probability whether or not to be selected in the second or the third sample. So that is why these are independent samples. So if there is a data point which went into the first sample, doesn't mean that it cannot go into the second or the third. So they are not dependent on each other. That is why it is independent sampling. Perfect. So basically means that each sample has been drawn independent of each other and sampling with replacement, which is what I mentioned as bootstrap sampling. And further, the sample size should be large enough. Ideally, more than 100. If not more than 100, at least greater than 30. That is where the constraint comes in. Okay, so please understand that. So if these three conditions are met, okay, IID and sample size, if these two, in fact, the very first had two conditions: independent, identical, and sample size. If these three conditions are met, then what? Then something interesting happens. According to the central limit theorem, irrespective of the original population distribution, the distribution of the sample means, see, let's have a look here. Okay, let's have a look here. So I have got various sample distributions and there is only one population distribution. Now I have got sample means here. I'm going to make a distribution of the sample means. So on this side, I have the distribution of the sample means. Once again, these are all KD plots. In Python, you remember about the KD plots, right? So these are all KD plots. So you have the red plot, which is the population distribution, and the other blue plots, which are the sample distributions. Fine. Now you are superimposing all those into one. So here, if you see, there is a range of the sample means, because all the sample means will exactly not be same, right? Because these are independent samples. So some sample mean might be 80, some sample mean might be 82, some sample mean might be 86, some sample might be 78, and so on. Whereas the population mean might be 81.5. So when you have a distribution of the sample means, so here the x-axis is not the sample mean. Here the x-axis, so if you see, what I have plotted is the distribution of the sample means. So what does the CLT say? See, the original distribution could be anything. It could be binomial, it could be Poisson, it could be geometric, it could be uniform, it could be normal. So the original distribution could be any of these. There is no constraint. So the statement says, irrespective of the original population distribution, the distribution of the sampling means always follows a normal distribution. So if I take the distribution of the sample means, I will always get a normal distribution, right? And the mean of that normal distribution is equal to the population mean. So that is something interesting. So I have drawn, let's say, 100 samples. From those 100 samples, I have got the sample means. If I take the mean of the sample means, I'll get the population mean. That is exactly what I mentioned here. And the last point is the standard deviation of the sample means is equal to sigma by root over n. Sigma divided by square root of n. Okay, so just remember this, sigma by square root of n. This is the first time you would be encountering this sigma by square root of n. And this is the core of hypothesis testing. All the hypothesis testing, you will have this term, sigma by square root of n, including the confidence interval calculations. So this is where it comes from. Okay, so that is the central limit theorem. So when you plot the sample means distribution, the mean of that distribution is at population mean, and the standard deviation, can you see the standard deviation of that sampling distribution is given by sigma by square root of n. See, sigma by square root of n can also be interpreted as the error in the estimation of the population mean from the sample mean. That is what I have written here. So if you want to estimate the population mean from a sample, how much error can you expect? That is sigma by square root of n. That is the interpretation. Once again, I repeat, if you want to estimate the population mean from the sample mean, how much error can I expect? That is sigma by square root of n. And one thing is very clear, as n increases, what is n? N is the sample size. If the sample size is 1 million, then sigma divided by square root of 1 million, okay, that is what? 1000, okay. So the overall quantity, the error will reduce to a very, very small number. Essentially, what you are trying to say is, if you take a very large sample, the estimation of the population mean from the sample mean will be very, very close to the actual population mean. So this error would be very, very small, right? As n increases, the whole quantity, that error quantity decreases. Sigma by square root of n represents the error in the estimation. So that error in the estimation will reduce. Fine. So I'll come back to this part, but directly now let's go to the hypothesis testing. So what are the steps involved? Okay. So number one, you have to define the null hypothesis and the alternate hypothesis. Okay. What is the null hypothesis? You should formulate the null hypothesis later. You should always formulate the alternate hypothesis first. So what is alternate hypothesis? So whatever your claim is, which is against the norm. Someone was commenting about the normal thing. Yes, the normal thing is your null hypothesis. If your claim is what everyone already believes, then you are going in sync with the null hypothesis. Your claim itself is the null hypothesis, right? So you have to make a claim which is against the norm. Okay. Then such a claim will become interesting to be validated. Then such a claim will be called as alternate hypothesis. Then comes the formulation of the null hypothesis. So how does the formulation of the null hypothesis happen? It is formulated in a way to nullify, okay, the alternate hypothesis, right? Fine. So just remember one more thing, that we have to make sure that the equality sign, because we have to convert these phrases into mathematical terms also. Okay. So once we convert this into a mathematical form, this will be a bit more clear. Okay. So the next step is to decide which test are we going to use, z-test, t-test, or chi-square test. Okay. Now we'll set aside the chi-square test discussion to the end. So there is no comparison of z-test with z-test, t-test with chi-square test. So just remember one thing, z-test and t-test, they are parametric tests. They are going to test a claim made on the population parameter. They are going to test a claim made on the population parameter. Chi-square test is a non-parametric test. So it is made to test something, completely different. Okay. So you are not even competing with z-test and t-test. Z-test and t-test compete. Okay. No, mostly people get confused whether to use z-test or t-test. Okay. So how do you identify whether to use z-test or t-test? Here comes the answer. If the number of data points within the sample is less than 30, go for t-test. Or if the standard deviation of the population is not known, go for t-test. In these two cases, easily go for a t-test. As simple as that. Otherwise, go for a z-test. So hypothesis testing that we are now going to do is for the population means. That is very clear. Okay. The step 3. Calculate the test statistic. Let's say I decided to go for a Z test. Then immediately I have to calculate my Z statistic. Or if I say that I want to go for the T test, then I'll have to calculate the T statistic. So this statistics will be chosen based on what test you are going to do. So if you are going to go for a chi-square test, then there is a separate formula for chi-square statistic. Okay. So that I will show you, that is there in my Jupyter notebook already. So mu naught is the hypothesized population mean. So I'll talk about that. Okay. So just make a note here. And then step 4 will be the critical value. So we'll calculate the critical value, or let's take an actual problem and these things will become clear. So I'll not get into all that, but let's take a actual business problem. I think I have it somewhere. Just a minute. The first problem, I'll just take it right away. Okay, I have a problem. Let me share my screen back. Okay, so let me maximize my screen. Okay, so the question goes this way, or the scenario goes this way. Let's say there is a passport office which claims that the passport applications are processed within 30 days of submitting the application form and all the necessary documents. Fine. I'll show you the data. That's a CSV file. So somewhere. So I have the actual data of the passport processing times. So can you see here the passport processing times? Okay. So of 40 40 applicants. So this data was collected. This data was collected. And now I am going to use that data in my Python code. Okay. So I have this data of 40 passport applicants. Now the population standard deviation is not known. Okay. It is not known right now. So conduct a hypothesis test at a significance level alpha. So what is alpha? Where will it come? I'll tell you. Okay. So let's go step by step. First, I said that you have to formulate the null and the alternate hypothesis. So for the first one, I am directly giving you. Okay. So what is the passport office claiming? That the average passport processing time, is less than 30 days. Okay. It's less than 30 days. So can you see this here? Mu is less than 30. So this is my alternate hypothesis. This is my alternate hypothesis. And mu greater than or equal to 30. So if the average passport processing time is greater than or equal to 30, then the passport office's claim will be nullified, right? When will this claim be nullified? When will this claim be nullified? So they are claiming that it is within 30 days. So less than 30, of course. So if the actual mean coming from the population is greater than or equal to 30, okay, then this claim gets nullified. So you should always formulate the alternate hypothesis first and then followed by the uh, null hypothesis. I think that point is clear. So now let me import this passport CSV file, and I'm just printing the mean and the standard deviation. So this is the mean passport processing time from the actual sample. So what I have in hand is the sample. Sample mean is 27.05. Sample standard deviation is 6.24. This is the sample standard deviation. Okay. And I have to calculate the test statistic. What is test statistic? The T-stat. So what was the formula for the T-stat? So that is X bar, which is the sample mean, minus mu naught, which is the hypothesized population mean. Okay. Divided by sample standard deviation. What is smallest? Sample standard deviation. Okay. And square root of n. Fine. So let me exactly use that. This is my sample mean. 30 is the hypothesized population mean. This is the sample standard deviation. And I have the square root of n. So I get a test statistic of negative 2.98. So this is the test statistic. Fine. Now what is the next step? You have to calculate a critical value. Okay. So this critical value will help us to uh, come to a decision. Let's say this critical value will help us to come to a decision. But to get to this critical value, you need a confidence level. Okay. Or to be more precise, significance level. Okay. Just a minute. I think. Okay, so this alpha is actually going to decide the critical value. The critical value will be decided based on alpha. Alpha is how much error you can tolerate in this entire hypothesis testing exercise. So alpha typically is taken as 5%. So there can be still a 5% chance that this entire hypothesis exercise, testing exercise can be erroneous. Conversely, 1 minus alpha will be the confidence level. So how much confidence do I have in rejecting the null hypothesis if there is no um, or very less evidence? That is exactly what your confidence level would be. Okay, so this alpha will decide the critical value. Let's calculate the critical value, and this critical value will kind of help us to come up to some decision. Okay, so in this case, the critical value is 1.644. Okay, now what does that mean? 1.644. Alpha is 0.05. I've already mentioned alpha is 0.05. Okay, so based on that alpha, I'm getting this. So let me just try to give you an interpretation here. Yeah, so does this work? Oh, okay, yeah, now it works. So okay, so what you have is somewhat like this. Okay, so here the population mean is always at 0. The sample, so this 27 will correspond to 0. Okay, this 27.05 will, sorry, no, not that will correspond to some value, which is this. So that is negative 2.98. So this negative 2.98 is your sample. This is your mu. So population, that 30 is actually corresponding to the peak. Okay, so that is your mu. Okay, so obviously it is lower. And how much lower? It is 2.98 standard deviations lower. That is what we are getting, that the sample standard deviation is 2. Okay, so this sample standard deviation is 2.98. Listen to me carefully. This time sample standard deviation is 2.98 standard deviations lower than the population standard mean. Okay, population mean. Sample mean is 2.98 standard deviations lower than the population mean. Okay, so I am looking for a critical value. So can I come up with a critical value? So critical value is negative 1.64. So negative 1.64 should be somewhere here, correct? That will be higher. This is 1.64. And the beauty is, beyond 1.64, we have the acceptance zone. Accepting what? The null hypothesis. And below that value, we have to reject the null hypothesis. So what I'm trying to directly imply is this 2.98, which is lower than your critical value. This is your critical value. So critical value is your cumulative probability. Okay, I'll just explain you. Okay, the critical value is also corresponding to the cumulative probability. So what is the cumulative probability? That is your alpha. So what you are saying is, you will accept the null hypothesis if there is 5% evidence coming from the data. Where is this 5% coming from? Alpha 0.05. No, that is why you are putting that alpha. Okay, so what you are saying is, even if there is a 5% chance, even if there is a 5% evidence in the favor of null hypothesis, I will accept it. But now the area under the curve, see, you had this area is 0.05. If you are still confused, this total area is 0.05. This total area, which I have now highlighted, is 0.05. You were looking for this much area, but what is the area you are getting in hand, my dear? You are only getting this much area, this much area. And you know how much is that area? This area is very small. So this cumulative area is now given by the next okay, so this 0.0024. So the actual area you wanted to accept is 0.05, but the area that you are getting is 0.024. Maybe I can clear this and show you once again. That will make it clear. Okay, so these are all steps mentioned in this. So if I go with that, flow, so what we did is you define the critical value and the decision making will depend on whether it is a left tail test or right tail test. But in any case, alpha is your minimum evidence needed in the favor of null hypothesis. That's very clear. Okay, alpha is the minimum evidence. So how much evidence do I need? 5% evidence. Okay, the actual evidence coming from the sample is called as p-value. The actual evidence coming from the sample is called as p-value. So alpha is the required evidence and p is the actual evidence. So if p exceeds alpha, what are you going to do? If p exceeds alpha, you have to accept the null hypothesis. So instead of accepting null hypothesis, we normally say that we fail to reject the null hypothesis. If the actual evidence coming from the sample is not even 5%, what will I do? I'll simply reject the null hypothesis. That is the whole idea. Okay, I'll simply reject the null hypothesis. Once again, what is the alpha? Alpha is the required evidence coming from the sample. Evidence has to be there, no? Evidence in the favor of null hypothesis. Always, we always look for evidence in the favor of null hypothesis, because entire hypothesis testing is all about validating or invalidating the null hypothesis. That is what my very first slide was saying. Okay, validating or invalidating the null hypothesis. So alpha is the minimum evidence I need in the favor of the null hypothesis, and p is the actual evidence coming from the data. So if the data is giving me more than the required evidence, I will accept it. Otherwise, I will reject it. It is as simple as that. Okay. So let me see if there are any questions. That is what I mentioned here. So P and alpha both are cumulative probabilities. So you would be using survival functions and CDF functions to calculate, depending on whether it is a left tail test or a right tail test. Okay. Let me check. There are questions here. Can we get Mayank? These are coming from any statistics books. So these problems are available in any statistics textbook. So don't worry, you can catch hold of any statistic. How to do that testing beneath, that is what I am discussing. Kendall is asking, how did we come up with greater than 30? That is again a standard knowledge base in any statistics book. So not venturing into that discussion. That's a very detailed discussion. Where is that 30 coming from? So any statistics book will give you that reason behind 30. Kindly explain sigma. Sigma was the population standard deviation. Okay. What is the difference? Mayur is asking difference between one-tailed, two-tailed. Okay. So one-tailed test is what currently we are doing. Two-tailed test is about the equality. So that another problem, the next problem will be a two-tailed test. So that will be clear from the next problem. Which tool are you using? I'm using Epic Pen. Okay. Abhishek is asking, two standard deviations would give 5% by no. So two standard deviations of the survival function. No. So Abhishek, do not confuse that with this. Okay. So here everything will depend on the critical value and the alpha. Okay. So let's see what we are doing. I mean, I can take your question once again, but probably I know you are trying to get that calculation in this. Okay. That can confuse very easily. Fine. So the decision making is very clear. All you have to do is just compare P with respect to alpha. The moment you have calculated the value of P, you will be able to compare that with alpha and immediately you have your decision. Fine. Why did we at all calculate the critical value? You can actually make your decision based on the critical value itself. That is also possible. Okay. So I can go back to the code and actually show you once again. Fine. So here I am just calculating the test statistic. That is the step number 2. First step is formulate the um, null and the alternate hypothesis. Second is identify what test are we going to use. Since here the population standard deviation is not known, I am going to use a t-test. Third step is to calculate the test statistic. So I calculated the test statistic. Fourth step is to calculate the critical value. So I am calculating the critical value. So this is my critical value. This is the critical. No, this is not the critical value. This is not the critical value. This is the critical value. Okay. This is the critical value. You have to, since you are talking about the t distribution, okay, you are talking about the t distribution. So this is the correct critical value. This is the correct critical value. Okay. So degree of freedom is 30 minus 1. So t distribution needs the degree of freedom. Okay. So this is alpha, that is your significance level. 40 minus 1, that is your degree of freedom. If you see, I can show you. It needs the degree of freedom. If you go down into the documentation page, so scipy.stats.t. I'm looking for CDF NSF. So if you go down, SF function, and that looks for DF. What is DF? Degrees of freedom. So you need to pass the degrees of freedom. Okay. So coming back. Okay. So this is my degrees of freedom. 41 is 1. So this is the, this is the critical value. Okay. Put this up. Okay. Now we are ready to make the decision. So basically t statistic here we are getting is, where is the t stat value? Can you see? Negative 2.98. So, and the critical value is negative 1.68. So I'll come back to that figure once again. So that will be easy now. So this is your 0. The critical value is this 1.68. This is my critical value. And the actual t stat is 2.98, negative 2.98. Okay. So as long as you are already in the rejection zone. I have already mentioned that. Okay. How do you define the rejection zone? Based on the critical. So the critical value will give you the boundary. So any t stat value greater than 1.68 will fall in the acceptance zone, and any t stat value lower than that, okay, will get into the rejection zone. So this is where I would reject my H naught, right? So right now you have 2.98, which is already in the rejection zone. Okay. So this is what I have also highlighted in the next figure. And I'll show you something interesting. So yeah, is this? No. There was some figure. Yeah. This one on the right side. Yeah. So this is a left tail test. So your rejection zone will be on the left side. In the case of right tail test, the rejection zone will be on the right side. In the case of a two tail test, you have two-sided rejection zones. So what is the meaning of rejection zone? That is the area, okay, covered until the test statistic. That is the area covered till the test statistic. Okay. Area beyond that will come in your acceptance zone. Okay. So coming back to that problem finally. So let me make our decision. Here we should be rejecting the, rejecting the null hypothesis. Very good. Because t stat is lower than the critical value. Now, another way you can make sure that you are doing the correct decision is calculate the p-values. What is the p-value? P-value is the actual evidence in the favor of the null hypothesis. How much evidence do you need? 5%. And how much evidence are you actually having? Convert that into percentage, 0.2%. And since P is less than alpha, hence again reject the null hypothesis. So both ways you are able to reject the null hypothesis. So this is just a cross check. If you don't want to do this, if it is confusing, ignore. This is very easy to interpret. So most people, compare P with alpha. That's it. So if you just do that way, that is perfectly fine. You don't have to take two comparisons for accepting or rejecting the hypothesis. Okay. So you can easily compare P value with alpha and accept or reject the null hypothesis very easily. So I'll take one more example. So as a follow-up question, if I assume that the population standard deviation is 12 days, how does the hypothesis testing look like now? Now, since I have the population standard deviation, this is a case of Z test. Why? Because the sample size is greater than 30. And now since the population standard deviation is also available, we'll be using Z test. Okay. So how does that change? So the formula is still the same. That is X bar minus mu divided by S. This time the S will be replaced by the population standard deviation. You will be using the population standard deviation. That's what I told you. Okay. So in the case of Z test, you will be using the population standard deviation. In the case of T test, you will be using the sample standard deviation. Exactly. Okay. Okay. So fine. So once I calculate this number, I get minus 1.55. Let me calculate the critical value for a Z test. So Z test critical value is negative 1.644. And what do you observe this time? So if I again go with that plot, okay, this time my critical value is at this 1.644. And that is your acceptance zone. Right side is again your acceptance zone. And you see that this Z statistic is at 1.55. This is 1.55, right? Sorry. This is 1.55. Which is negative. Yeah. So you are already in the acceptance zone. You are already in the acceptance zone. So in this case, the same problem, the entire scenario changed. You see, the entire scenario changed. And you can verify that. You see, you have almost 6% evidence. You fail to reject the null hypothesis in this case. Why we fail to reject? Because we have more than the needed evidence. How much evidence did we need? 5%. And how much evidence we are actually having? 6%. Just multiply that by 100, it becomes percentage. So we have 6% evidence coming from the sample. Okay. Whereas the required evidence was that 5% only. Okay. So you are comparing critical value. This critical value is greater. Yeah. So Z statistic is greater than the critical value this time. Do you see? 1.55 negative is greater than minus 1.644, which means that you fail to reject the null hypothesis. You are already in the acceptance zone, right? So that is how you would be doing the Z test and T test. And one interesting thing I'll tell you that if you increase the sample size in the case of a T test, it will actually converge to a Z test without proof. But remember that whether you go for a Z test or a T test will not make any difference if the sample size is already in thousands, at least in thousands. It has to be close to, let's say, 10,000. If the sample size is more than 10,000, then there will be no difference, almost no difference within whether you are doing a Z test or a T test. Okay, so whether you use T distribution or you are using Z distribution, that will not make not much of a difference, right? Okay, so how much time we have? We are already exceeded. So I can continue provided the audience is there. I have that liberty. Or I can wind up here. If you want to see, I had actually planned 6 exercises, 4, 5, and 6. Now these won't take much time because the basics are already done. I just want to see the audience view. Okay, if you want me to continue, because this will anyway be there in the recordings, you can catch up from there as well if you want to hurry up. I know covering so much things in a small span of time is extremely difficult. Okay, I might have overcommitted, quite possible. Okay, but I'm just trying to take care of the wide range of audience who were completely clueless about these terms, and these terms will become clearer and clearer as we are taking more and more problems. Okay, so let's take another question here, another problem statement. Okay, so according to some IQ research company, again, some random name I have given. Okay. And these are again numbers. Please do not take it by, yeah. So the intelligence quotient of Indians is, let's say, 82, derived based out of some research by some random professor name I have taken. And between the data collected between this and this year, doesn't matter. Now the population standard deviation of this IQ is estimated to be 11.03. So there is some scale. So in that scale, the average intelligence quotient of the Indians is estimated to be 82. So some test was given based on that questionnaire. The estimated value was 82. Okay. And the standard deviation came out to be 11.03. Okay. Thank you guys. Thank you. Now, based on the sample of 100 people, the IQ was actually estimated to be 84. Now, this is the ground truth. This is the ground truth. 100 people, estimated value is 84, but the claim made by the company is 82. You see here. Once again, this is the value coming from the actual data. 100 people were surveyed and the sample mean was 84. The sample mean was 84. The company is claiming that it is not, no, 84 is too high. Probably the sample is biased. I think that the mean for the population is less than 84, let's say 82. So they are claiming something about the population. See, claim is always made about the population mean. Things will get clearer. Okay. So the claim is always made about the population mean. Remember that. Okay. So in this case, how do you conduct a hypothesis test to validate the claim made by the IQ research company? So, okay, I'll help you. So let's say, what is mu in this case? Mu is defined to be your population, population average. So average IQ of the population is your mu. So now the null hypothesis will be mu something equal to 82. This is what the company is claiming. Okay, this is what the IQ research company is claiming. IQ research company is claiming. So always remember that the equality sign, claiming, okay, right, will always go with the equality sign, will always go with the null hypothesis. So what is the alternate hypothesis? When is this going to get invalidated? Sorry. So HA will be, in this case, HA will be not equal to 82. Simple. Now, what do you mean by not equal to 82? So it has to be close enough, right? It cannot be exactly 82. It can be 81.5. It can be 80.5. It can be 75. Or on the higher side, it could be 82.5. It can be 85. It can be 90. But how much less and how much more can I tolerate? So you have to have two rejection zones. How much less and how much more can you accommodate, right? Exactly. So that is why we have two rejection zones. So this much tolerance I have. The white zone is your acceptance zone. So the value may not be exactly 82. Even if it is 82.5 or maybe 81.5, I am ready to accept it as 82. That's what you are trying to say. But if it is, let's say 90.5, now that is very far from 82, it will automatically go in the rejection zone. So I'm not going to tolerate 90.5 and take your claim. Okay. But if the value is slightly less or more than 82, it's still well within the acceptance zone. Exactly. That is the whole concept of having two rejection zone, one on the lower side, one on the higher side. So all you have to do is just compare it from one side and that is fine. So this 5% is the cumulative probability for rejection in total. Okay. Cumulative probability for rejection in total. So one half of that alpha will be on the lower side. One half of the alpha will be on the higher side. Okay. So you are going to compare your p value with alpha by 2. Okay. So that is one big difference. This case, the population deviation is known. So I can directly go for a Z test, directly going for a Z test because the population standard deviation is known 11.03. And what is the formula that I'm using? Once again, X bar minus, come on, X bar minus the hypothesized population mean divided by sigma by square root of n. Same formula I'm using here. Population mean is hypothesized to be 82. Sample is giving me 84. 11.03 is the population standard deviation already given in the problem, and the sample size is 100. So when I execute this, the Z statistic is coming to be 1.81. Perfect. Now all I have to do is get the critical value. So critical value will be obtained by taking half of alpha. Okay, so either you compare it with half of the alpha, or still better, you compare the p-value with alpha by 2. Let's compare the p-value. That's much easy to interpret. So how much evidence do you need on one side? Half of 5%, that is 2.5%. Is this exceeding 2.5%? Is this exceeding 2.5%? Tell me, yes or no. Is this exceeding 2.5%? Yes. And so you fail to reject. You fail to reject the null hypothesis. Absolutely. Or if you want to compare with the total alpha, then you have to double that p-value. You have to double that p-value to compare it with the total alpha. So your total cumulative evidence coming from this sample is 7%, roughly 6.97, close to 7%. So you have 7% evidence in the favor of null hypothesis. So you again fail to reject the null hypothesis. Sorry. You again fail to reject the null hypothesis. Okay. This is how you can do the hypothesis testing quickly. So it is all between the P and alpha, P and alpha. For each of the problem, you just have to calculate P and alpha and immediately come to a conclusion. It is actually that simple. Okay. The only crux is which test to use, what formula. This is all there in the notebook already. Okay. So this is the case of a two-tailed test. So in the two-tailed test, the claim is made about the equality, not less than or more than. That is the case of a left-tailed test or a right-tailed test. So I can quickly tell you once again. In the right-tailed test, the claim is made about the population parameter greater than something. So let's say I make a claim that the average salary of data scientists is greater than $100,000. Then my claim will be validated by using a right-tail test. It is that simple. Once again, I repeat. Is that simple? Yes or no? Now, is that making sense to you? I am claiming that the average salary of the data scientists is greater than $100,000. That is exactly a case for a right-tail test because the claimed population mean is greater than something. If the claimed population mean is less than something, it's a left-tail test. You remember the passport office is claiming that the average passport processing time is less than 30 days. So it's a case of a left-tail test. Whenever the claim is made about the equality of the average population mean, okay, then it is a case of a two-tailed test. That is exactly you have to. So I'll just highlight one more point here. The equality sign always goes with the null hypothesis. It's very clearly mentioned in this. Okay. So if the company is making a claim about equality, then the company's claim itself is the null hypothesis. Someone had a doubt. I read it in the chat box. Okay. Now, is that very clear to everyone? So if you are making the claim about the equality of the population mean with some number, then your claim itself will be taken as the null hypothesis. You are very much in line with the null hypothesis. So that's the case of a two-tailed test. Very good. Now comes a bit more interesting example. Okay. This is very interesting example. Very interesting. In fact, really. Okay. Let me first give an overall context. When would you go for a paired sample test? Now, there are two variants of the paired sample test. that is independent and dependent. So when would you go for a paired sample test? Because here I'm not presenting any scenario or any theory or any text here. So you just have to listen to me. Okay. So in many cases, we would like to analyze whether some experiment or some intervention or some treatment. Okay. Okay, what do you mean? Maybe I can give you some example. Let's say there is a training program. Just imagine a training program. Okay. So I have set of 30 students. So what will I do is, before the training program, I'll take a assessment. So that's like a pre-training assessment. So let's say there were 30 students and I got an average score of, let's say, 70 out of 100. Average score of 70 out of 100. That is prior to the training program. After the training, the same set of 30 students are undergoing another test. That is a post-training assessment. Now the average marks is coming out to be 75. Now I am claiming that the increase in the average marks is due to the training program. That tends to mark the success of training program. You understand? The same set of 30 students gave a test before the training program. The average came out to be 70. Now the same people are undergoing training program, and after training, the average test marks was 75. Now I am making a claim that this increase of 5 marks is due to my training. Or is it just a random occurrence? Is the point I'm trying to validate here. Is this increase of, listen to me very carefully now, is this increase of 5%, of 5 marks, sorry, statistically significant to make such a claim? Okay. Is this increase of 5 marks statistically significant to make a claim about the success of the training program? Am I making sense now? So let's say you have X sales on a weekly basis on an average, and then a discount campaign was run. Okay. So you have X amount of sales coming up, or X number of sales for a particular product on a website, e-commerce website, coming up on a regular basis. Let's say weekly average is X. And now the company decides, let's go for a discount offer for 1 week. Let's say Friday sale, or anything, Black Friday sale, 1 week we will run 20% flat discount, and you get some X plus delta. X plus delta. Now the question here is that delta significant? That is what you are going to test in a paired sample test. Now, is that scenario clear? I can give you more examples. Absolutely. So you can think about the body weight of subjects or patients before and after attending a yoga training program, or cholesterol level of the patients maybe before and after a meditation program, or the average time spent by subjects on internet before and after marriage. Okay. Or quantity of the alcohol consumed by people before and after breakups. That is the exact exercise I'm going to discuss. Okay. Am I making sense now? Okay. Once again, I repeat, the quantity of alcohol consumed by people before and after a breakup. Okay. Or even the level of cortisol among students during and after the exam. So same set of students are undergoing test before and after an intervention. Okay. So you will get two averages. Question is, are these difference between the average values statistically significant? And that is the point I am trying to, justify in this. So we have some assumption. So let us assume that the differences follow a normal distribution. So all the noise is gone now. We are only 50 people who are really interested in hypothesis testing. All the noise of the first 50 is gone. So now we have the real data set to work and model building. You see 50% churn rate. That's okay completely. They might be having other commitments. Okay. Or they might be interested in the a subsequent DataHour session also that is also going on. Someone pointed that. That's okay, completely fine. So this is the formula, okay, T-stat. Why we are talking about T-stat? Because all the metrics you are going to calculate from the same sample, right? So we have to go for a T-stat. Okay. What is capital D? Capital D is the main difference in the estimated parameter value before and after a treatment. In this case, breakup or whatever. And sigma D is the standard deviation. Okay. And hypothesized mean difference. So let me take a practical example and that will make sense. Okay. So the data shows, where is the data? I'll just show it. Yeah, so I have imported that data now. Okay, zooming out. Now you can see the weekly alcohol consumption in milliliters before and after the breakup. Now we have to conduct a paired sample t-test to check whether this alcohol consumption is more after the breakup. Normally, this is what people would expect. Yes or no? Yes. This is what normally people would expect. Let's see whether it is coming from the data as well. Do we have enough evidence in favor of this hypothesis? What is the hypothesis? People tend to drink more after a breakup. That is a simple hypothesis. I want to validate this exactly from this data set that we have. Okay. So I've imported this file and I've calculated the difference as after the breakup minus before the breakup. Basically column 2 minus column 1. So this is the difference I calculated. Fine. How many data points do I have? 20 people. So I just took a survey of 20 people. Not so that is another reason I'm going to use the t-test in this case, because the sample size is not big. It's a small sample size. Fine. Now let's calculate the mean of the differences. So now is that clear? What is capital D? It is the mean of the third column here, this difference column, mean of the difference column. So the average difference, essentially, what is the average difference? And what is the standard deviation of the differences? So the standard deviation of the differences is 96 milliliter roughly. And the average difference is 11.5. Yeah. And N is the sample size. Why will I need this N? Why will I need this N? Degree of freedom. We want to calculate that. But is this clear to everyone till here? Right? These calculations. So capital D is the average difference. SD is your standard deviation of the difference, standard deviation of this third column. Okay. Now when you substitute, you'll get the test statistic. Here mu will be taken as 0 because we are only talking about greater than this. Okay. So if this is greater than this or not. So mu is 0 as of now. I'm not saying greater by this much amount. If I say the people are drinking 100 ml more on an average after the breakup, then the mu will be 100. Right now mu is 0. Right now mu is 0. Is this clear? Why did I take it to be 0 here? Once again, I repeat, if the claim was that after the breakup, people drink 100 ml more than the before the breakup, then this 100 will become your mu D. That is the hypothesized population mean, right? Right now, it is 0 because my claim is only that they are drinking more than the more after the breakup compared to the previous. Fine. Now, can we come up with the hypotheses now? So what are the hypotheses? Come on. Can you guys help? What are the hypotheses? So first, you should go with the mu always. Mu greater than 0. And here, mu will be less than or equal to 0. Please convince yourself. Is that making sense? If mu is greater than 0, what is mu? Mu is the difference between after breakup and before breakup. That is the mu. Okay, mu is referring to the average consumption after breakup minus average consumption before breakup. That is your mu. Okay. So you are claiming it to be greater than 0, which means average consumption after breakup is more than the average consumption before breakup. Correct? So when will that get invalidated? When will that become invalid? When will that become invalid? When the average consumption is actually less or equal. Make sense? So less than or equal to will invalidate that claim. Very good. So now this differences, you will get this statement in the statistics books that this difference, this column, again, I cannot annotate, but this difference follows a t distribution with degree of freedom n-1. This difference follows a t distribution with a degree of freedom of n-1, right? So that is what I mentioned here. It's a t distribution with n-1 degree of freedom. So just substitute the values and what I get is this. This is a t stat. So with that t stat, I have to compare, and it's a right tail test, right? Do you guys agree? Because your claimed population mean is greater than something. So it's a right tail test. Let me put it here itself. It's a right tailed test. Okay. What is the critical value here? Critical value is this. So can you give a decision here? In a right tail test, what do you want? In a right tail test, what do you want? In a right tail test, let's say this is a critical value. Okay, this is 1.729. 1.729 is your critical value. So this becomes your acceptance zone and this becomes my rejection zone. Okay. So beyond this will be my rejection zone. And where is this guy? T stat. Where is this T stat? This is our mu. That is well within the acceptance zone, is it not? 0.53 is well within the acceptance zone. It is already within the acceptance zone. It is already well within the acceptance zone, correct? It is already within the acceptance zone. This is the acceptance zone. So this is your rejection zone. This area is your rejection zone. So beyond the critical value always is your rejection zone. Is that clear? That has always been happening. Beyond that is your rejection zone always. Okay. So you are very well within the acceptance zone. What does that mean? You are going to accept the null hypothesis. So essentially, I'll just copy one statement here. You fail to reject the null hypothesis. Normally, we don't say accept the null hypothesis. We normally say fail to reject the null hypothesis. Sorry, fail to reject. So I come up with my decision, fail to reject. And can that be validated by P? Perfect. I have roughly 30% evidence, not just 5. I have 30% evidence. That's a huge amount of evidence. So very confidently, I can reject the null hypothesis. Oh, sorry, accept the null hypothesis. Okay, because we have huge confidence. So we have 30% evidence in the favor of the null hypothesis. So very confidently, we can reject the alternate hypothesis. What was the alternate hypothesis? Can we go up and see? Here it is. So whatever you guys were claiming that people tend to drink greater or more amount of alcohol after breakup, that statement is not validated now. In this case, there is enough evidence in the favor of null hypothesis. There is enough evidence in the favor of null hypothesis. So we fail to reject the null hypothesis. And hence it means that there is not much of a significant difference. See, what does the null hypothesis say? In words, there is not much significant difference. And you are claiming that there is a significant difference. I think that is very clear, right? Perfect. Last two cases quickly. So now if you want to compare two different population means altogether, and when the standard deviation of the population is known, you can go for a 2-sample Z test. Once again, you can compare two population means. So two different populations altogether. And you are comparing the population standard deviation, population means, and the population standard deviation is also known. In that case, you can use the two sample Z test. If the population mean is not known, that scenario is there here. So population standard deviation is not known, then what to do? So if it is known, go for a Z test. And this is the formula that you would be using for calculating the Z statistic. Okay. Here the Z statistic in the equation below is valid only when the population standard deviations are known and the samples are from a normal distribution. So there are two assumptions here. Sample is also coming from a normal distribution. Fine. Perfect. So I've given a scenario here. Let's quickly take that. So the dean of some management school is believing that the graduating students with a specialization in marketing are earning at least 500 rupees more per month than the students with the specialization in operations management. Now, to verify his belief, the dean collected the sample data from the graduating students, which are mentioned in the table below. Conduct a hypothesis test with alpha of 0.05 to check whether the difference is at least more than 500 for marketing specialization compared to the operations. So this difference of 5,000 has to be statistically significant. And that is what we are trying to, justify. Now, these two are two set of different students. Okay. The same student is not learning marketing and the same set of student is not learning operation management. So that is the reason we have two different populations. Is that clear? Why we are talking about two different populations? Because you are drawing two samples from two different populations. So what is the population mean here in this case? Population means in this case, the pool of all the students from all the B schools from the entire country who are studying marketing. That is the complete population. Okay. Similarly, another population is constituted by all the students of all the B schools of the entire country who are studying operations management. And now you are taking a sample of these two populations. Okay, so what are these numbers now? X1 bar and X2 bar. What is X1 bar? X1 bar is the first sample mean. X2 bar is the second sample mean. So you are drawing two samples from two different populations, correct? And so what is mu1 and mu2? The actual population means. So mu1 is the first population mean, mu2 is the second population mean. What is X1 bar? That is your sample mean. So two samples drawn from two different sample populations, sorry. And the population standard deviations are also known. So what is sigma 1 and sigma 2? These are the population standard deviations. What is N1 and N2? These are the sample sizes. So sample sizes, right? So you may not have equal number of students, right? In marketing and operations management, marketing is more popular. Almost every B school will have marketing. So the population size is definitely expected to be higher for marketing than for operations management. So this is N1 and N2. Maybe I can just quickly annotate. So this is N1, this is your N2. Okay. And this is your X1 bar. This is your X2 bar. And this is your sigma 1 and this is your sigma 2. Is that clear? All the numbers? All the numbers are clear. I just have to plug in my above formula and immediately I get the Z statistic value, correct? So one has to understand the business problem and then come up with the numbers. And then things become very simple. Okay. Perfect. So can you tell me what are the claims here? If you have understood, can we write down the claims? So in this case, you are claiming that mu1 minus mu2, mu1 minus mu2 is greater than 5,000. That is the claim made by the dean of some random institute here, and less than or equal to will be nullifying the claim made by the dean. Does everyone agree on this? This is what a dean is claiming, right? That marketing people or marketing students on an average are getting 5,000 salary more than the operations management guys. So when is the claim invalidated? When it is less than or equal to. As simple as that. right? And is it a right tail test or a left tail test? Quick. Is it a right tailed or a left tailed? Perfect. It's a right tail test. Okay. So again, you would be using which function? Survival function and inverse of the survival function. That's it. So when I plug in all the numbers, okay, I get 3.73 as the Z statistic. It's a right tail test. And what is the critical value? Everyone knows, right? 1.64. Every time it is. Please remember this number now. Okay. For a alpha of 0.05, critical value is 1.645 plus or minus. Okay. Once again, I repeat, for a alpha of 0.05, critical value of Z will always be 1.645. You don't have to calculate it every time. I can show you. Here also you calculated it. Sorry, this is a t-test. So 1.645 somewhere you calculated here. No, this is 1.96 because this is alpha by 2 you have taken. So here you can see 1.6448. 1.6448. So remember that the value would be negative or positive depending on whether it is a left tail test or a right tail test. So that won't change the value as such. Okay. But the number will always be constant, 1.645. Remember that. Fine. So I am directly able to compare 3.73 from 1.645. See, what does the critical value physically mean? Okay, listen to me carefully. The critical value is trying to say that I am ready to accept the null hypothesis if the sample standard deviation is within 1.645 standard deviations from the mean. Mean is at the peak. Right now you are 3.73 standard deviations. You are very far from the acceptance zone. Acceptance zone is 1.645. So you can tolerate up to 1.645 standard deviations away from the mean. But here the sample mean is 3.73 standard deviations away from the mean. It is very far from the mean. So sample does not have that evidence. So what do you do when the sample does not have that evidence? You reject the null hypothesis. So is this interpretation now making sense? Okay. You are 3.73 standard deviations away from the mean. How much can I tolerate? 1.645 standard deviations I can accept. If it is coming beyond that, then I will reject. Then the sample does not have enough evidence in the favor of the claim. See, the claim will always be validated or invalidated based on the sample. Sample has to produce the evidence, right? If the sample does not have that much amount of evidence, the sample is very far from the reality. What is the reality? Reality is at 0. Mu is at 0, no? That is a population. So reality is at 0 and the sample standard deviation is 3.7 standard deviations away. Perfect. So one more scenario here. So here, see, the scenario is not very different. The only difference between this example and this example is the standard deviations of the populations are not known, but are assumed to be equal. That is the only difference. And then we talk about the pooled sample variance. Okay, but they are believed to be equal. Okay, I don't know what is the population standard deviation of each of the two populations, but I would assume it to be equal. In that case, you will calculate the pooled sample variance. You will calculate the pooled sample variance and you will conduct a t-test. Obviously, you will go for a t-test. So where will you use this pooled sample variance? Can you see closely? I'm using it here. So this is being used here. So this is a pooled sample variance. Pooled sample variance is this. This is a pooled sample variance. So what is S1 and S2? These are the sample variances. S1 square and S2 square. Can you see? These are the sample variances. What are N1 and N2? These are the sample sizes. What is X1 bar and X2 bar? These are the mean values coming from the two samples. And what is mu1 and mu2? These are the claimed population means. So do I have a problem for this? Yes. So a company makes a claim that the children in the age group between 7 and 12 who drink their health drink will grow taller than the children who do not drink that particular health drink. So the table is showing that the average increase in height over 1 year time period from the two groups. Okay, 1 year time period from the two groups, two different populations are there. And I don't know their standard deviations, but I'm assuming it to be equal, right? So which are the two groups? One group is taking that health drink every day. The other group is not taking their health drink at all for the period of 1 year. Now with the alpha of again 0.05, I have to test whether the increase in height is really statistically significant. Unless that increase in height is not statistically significant, the claim made by the company will be invalidated. When it will be statistically significant, so some authority says that it has to exceed this. So the average height of those students or children who are taking the health drink, the average height has to exceed, has to be more than 1.2 centimeter, more than those people, those children who are not taking that health drink. Does that make sense? So this time I have given a number. I'm not saying simply more. It has to be more than some number. So this will be your mu. Mu1 minus mu2, in fact, that will be your mu1 minus mu2. So now you have the group sizes. Can you, maybe I'll take a pause and tell me what are the alternate and the null hypothesis in this case. What do you think? Quick. I think it is very, very simple. So I've taken a lot of time, but now I'm enjoying. Less people, less noise, more attentive audience, and more responsive audience. Okay, good. Everyone would agree? Everyone would agree? That difference has to exceed 1.2 centimeter. That is the main point. That difference has to exceed, my dear. It has to be at least 1.2. So it has to exceed. At least means it has to exceed. So is it a left tail test or a right tail test? Once again, it's a right tail test once again. So I can directly calculate. So this is the number I have just calculated. I'm not spending time in calculating. So this is the number. Is everyone clear where this number came from? This number is coming from this formula. Okay. This number is coming from this formula. Where is it? This formula. Okay. So it's coming from that formula. Fine. So I can just directly compare that T stat value, which I got here, with the critical value. So what is the critical value? 1.654. This time I have to calculate. Why? Because this is a T distribution. And this time the T distribution, see one more statement I think we missed is this part. It's a T distribution with a degree of freedom of N1 plus N2 minus 2. Why minus 2? Can you tell me now? Why minus 2? Why minus 2? Because not just two groups. From each group, we are estimating one parameter. Which parameter? Standard deviation or the variances. Can you see the sample variances are being estimated from each of the two groups? No. So these are the two parameters which are being estimated. Is that clear, everyone? Why it is decreased by 2? So two parameters you are estimating from your two samples. Okay. And that is why it is N1 plus N2 minus 2. Degree of freedom has reduced by 2. Ideally, the degree of freedom will be equal to the number of data points, but it will keep reducing as you extract more parameters from the same sample. Fine. So what is your decision then finally? Yes, everyone. Reject, fail to reject. This is fail to reject. Perfect. This is fail to reject. Because it is well within the acceptance zone. It is, I would have rejected it if the T stat was exceeding 1.65. I have a tolerance till 1.65 standard deviations, right? Now it is only within 0.5 standard deviation. So it is well within the acceptance zone. So you fail to reject the null hypothesis. Indirectly, you accept the null hypothesis. Perfect. Awesome. Okay. So enough. I'll take another maybe 5 minutes to do a quick calculation on the confidence intervals. Okay. So this is something very interesting. So what have we been doing? I'll just summarize that in this quick screen here. So what have we been doing? So we had some samples from the population. Okay. Let's say we have some sample. Now, once we have a single sample, let's focus on a single sample. Okay. Once we have a sample, we can do two things. We can do two things. From that sample, either we can estimate or guesstimate, whatever word you want to use. We can estimate the population mean from the sample mean. See, you have the sample. You have the sample. So from the sample, you can get a sample mean. And using that sample mean, you can estimate the population mean. See here, I'm not proposing anything. I am actually guessing or calculating. Okay. That is called as estimation. So I'm estimating the population mean, or I could estimate the population variance, or I could estimate the population proportion. One of these three parameters. So you're estimating the population mean from the sample mean. That estimation will lie within a band. Thank you, Sanjay. Thank you. Yeah. That estimation will lie within a band, which is called as confidence interval. So it has to be plus minus some number. So how much plus, how much minus, that is given by your Z alpha by 2. And we know that the Z alpha by 2 is a critical value against alpha by 2. That is the critical value against the alpha by 2. And sigma by square root of n, anyway, you know it. The other way around is what we have been doing. I don't want to calculate the population mean. I just want to hypothesize something and then see whether my hypothesis is making sense or not. You can just read this. You can directly hypothesize a value for the population mean from the sample and try to validate this number. That's what we have been doing in all the 6 exercises, right? Some company or some agency or someone is making a claim about the population. And then we are trying to validate or invalidate that claim. We are not estimating it. Now we are going to estimate it. Is this very clear? These two things. In one case, you are calculating the parameter value. In the other case, you are proposing some value and checking if that value makes sense or not. That is the clear differentiation between confidence interval estimation versus hypothesis testing. So these are the two things you can do the moment you have a sample in hand. Okay, perfect. Let's go back. Let me take a sample. This is the same Titanic data set. I'm not taking any exotic data set in the interest of time, because if I take any exotic data set, I'll have to spend another 10 minutes in explaining where this data set came from, what this data set conveys, this and that. I hope this is very clear to everyone, right? I completely wanted to avoid that discussion. Fine. So I've taken a very simple data set which everyone would have seen in their lifetime. Okay. So I really do not know the sample, the population mean. Right now, I don't know the population mean, correct? So I take a sample of 100 people and then take the average of those age. Fine. Is this clear? What did I do? I took a small sample of 100 and I'm finding the average of that. So what is the average coming as? So every time this will keep changing. So let it be 31.66 right now. This is 31.66 is the sample mean. It is the sample mean. Sample is always random. Nani, okay, sample is always random. That is the definition of the sample. Sample has to be random, right? Perfect. Because every time I run this, I'll end up with a different number. That clearly tells you that the sample is random. So random 100 people were drawn. And out of how many? 891. You can see the size of the data frame. df.shape. So 891 people. Out of that, I pulled out 100 randomly and just took their means. I don't know the population mean. I have just commented this out. Let this be suspense. Let there be some suspense. Okay. And I want to estimate this parameter. Fine, everyone. I want to estimate this parameter from the samples. Okay. Now see, where is this scenario going to be helpful? Let me give you a scenario here. You have 1 billion data points, which is expanding to 200 GB. Now, if you have 200 GB data, which is having 1 billion data points, and you want to calculate the mean of a particular feature, you want to calculate the mean of a particular feature. See, that mean calculation itself will take you hours because the number of data points is huge. What you can do is you can pull a sample from that data set, not one sample, some more samples. Let's say I took 50 samples, smaller in size, and I'll apply my central limit theorem. What does the central limit theorem say? What does my central limit theorem say? Right? The mean of the sample means will be very, very close to the population mean. Right? That is exactly I'm going to validate now. Okay, so we want to estimate the population mean from the sample mean. And for this, we can calculate the 95% confidence interval. Okay, so this is your norm.isf. That is your Z alpha by 2 I was talking about. Critical value against alpha by 2. It is as simple as that. 1.96. Remember, we had got that. Okay, I'll not go up, but somewhere it was already there. Critical value against alpha by 2, two-tail test. Yeah, here you can see 1.96. Can you see 1.96? So it is 1.96. That is norm.isf alpha by 2. It's the same number which I'm using here. Okay. Same thing. Norm.isf alpha by 2. So this is going to be 1.96. Perfect. Now this is your mean. Standard deviation coming from the sample or the population. This is coming from the population. Very good. Very good. When the DDoF is 0, it is coming from the population. When the DDoF is 1, it is coming from the sample. What is DDoF? DDoF is the difference between n and the degrees of freedom. I'll go back to that. Okay. Somewhere I had mentioned that. DDoF I had mentioned. Yes. DDoF is the difference between n and degrees of freedom. That is n minus k. Okay. So when I say k is 0, what does that mean? When k is 0, that means we are referring to the population directly. When k is 1, we are referring to the sample, right? So we have to take correct. And then divided by the square root of the sample size. Perfect. Sigma by square root of n, sigma by square root of n. That was the formula. So this is your sigma. That is a population standard deviation and square root of n. Awesome. So I'll get some number. Let me print that number. Okay, that is the lower side. What is the upper side? This is your upper side, 24.969 something. Okay, this is your upper side. So if you want, you can repeat the same exercise once again, doesn't matter. So you'll get 27.32. Let's freeze with one of the samples. So let's say I've taken this sample, doesn't matter. So 27 and 32 is what I have taken as the sample. Now the confidence interval of 95%, what does that mean? If I repeat this exercise 100 times, see, this is the second iteration. In the first iteration, this value was 27, this value was 24, this value was 29. Just few seconds ago. The second iteration, this is 29, 27, 32. In the third iteration, again the numbers will change. Again the numbers will change. If I do this 100 times, then 95% of the times, the population mean will lie in this range, 27 to 32 or whatever that is, okay, will lie in this range. That is what we are trying to claim. That is what the confidence interval conveys. Okay. Then 95 out of 100 times, the population mean will lie between the confidence interval. And there is still a 5% chance that the population mean may not lie in the confidence interval estimated. So you are estimating a confidence interval. You are estimating a confidence interval. Okay, let's see that. So we are drawing 100 samples now. I'm using a list comprehension and I'm drawing 100 samples. And those 100 sample means are stored here. If you want, I can show you. So these are the 100 sample means. Okay, these are the 100 sample means. You can see that the sample means are varying. Now, if I plot these sample means, I'll get a normal distribution. Why? Because that is the central limit theorem. That is the central limit theorem. The plot of the sample means will be a normal distribution. That is exactly the center limit theorem. Okay. So if you waited till this point, I appreciate it. So let me just plot that. I'm just taking a histogram. See, it resembles. It is just a histogram. If I plot a KD, it will be even very smooth. See, no bluffing. It's all there, right in front of you. Okay, so this pretty much normal distribution. That is exactly what central limit theorem was conveying. Okay. That is the beauty of the central limit theorem. Okay. I did not assume any. See, I don't even know what is the distribution of the age. In fact, that is not normal. Let me tell you. If you plot the age, the original population age, that is skewed, and that too heavily skewed. If you don't believe, let me just plot the original population distribution. Okay. That is DF, and then age, and then okay, let's take the histogram. From there also you can clearly see there is skewness. You can clearly see there is skewness. So it is shifted on the right side. So it is not symmetric. So it's not a normal distribution actually. Okay, it's not a normal distribution. That is the population distribution. It is right skewed. Absolutely. These are continuous values, Nani. Okay, age we are assuming it to be a continuous variable. Now let's come to the final thing. This is my final thing. What is the actual mean of the samples? See, this is the mean of the samples. Ready? This is the mean of the population. This is the mean of the population. Awesome. This is the mean you are getting from 100 samples. So the sample means, the mean of the sample means is very close to the population mean. That was exactly what the central limit theorem was saying. You guys remember? Got the goosebumps? Okay, this is exactly what central limit theorem is saying. So if you draw multiple samples from the same population and plot their sampling means, that sampling means will be a normal distribution, and the mean of the sampling mean will be very close to the population mean. And the third point was the standard deviation of the sampling mean will be sigma by square root of n. Absolutely perfect. See, so I mean, theory and practical cannot be different. If you provide enough time, literally things are all easily demonstrable. But if you try to understand entire process of hypothesis testing in 1 hour, that is an oxymoron probably. Okay, and this last piece of code, I'll skip the chi-square test for some time later. Okay, I'll keep this discussion for some time later. Okay, so this is my last block of code, and you will enjoy this last block of code. Okay, you'll enjoy this last block of code. Why? Because I'm going to find out something interesting. This is the population mean. Okay, listen to me very carefully. I am going to be very critical now. Okay, this very last part. 29.29 is my population mean, and these are the bounds. You understand? I had drawn 100 samples, and from each of the sample, I am estimating a confidence interval. Is that clear? What are these, guys? What are these numbers? These are the confidence intervals being estimated from each of those 100 samples. And then what did I say? What I said is there is still a 5% chance. Snehal, just one moment. Okay. So there is still a 5% chance that the estimated population mean may not lie in this interval. Let's see. Let's see. This is almost at the boundary. This is almost again at the boundary. This is also again at the boundary. So this is strange. This time I have got, this is also at the boundary. So almost at the boundary, we have got 2, 3. But at least we should be able to get one scenario where this is again at the boundary. where, we got it. We got it. See, this is your confidence interval estimated from sample. So we have got one sample. There might be many more. Okay. So we have got one sample as of now, whose estimated confidence interval is 29.99 to 29. Your actual population mean is 29.29. That does not lie within the estimated confidence interval. That is exactly what I was trying to demonstrate. Is this clear? And this can happen 5 out of 100. This can happen 5 out of 100. So you are lucky that it has just happened once right now. Is there second? See, this is the second case. Second case, we got another one. So 2 cases we have got. See, maximum you can get 5. Maximum you can get 5. You can get 1, you can get 2. We have got 2 cases. Any more? Okay, so we have got 2 cases. So that's what. So there can still be a 5% chance, max to max, that the estimated population mean may not lie in that confidence interval. And that demonstration I just now did. We have got not one but 2 scenarios where the the actual population mean does not lie within the estimated confidence interval. The actual population mean is 29.29, and that is not lying in this interval. Again, this is not lying in this interval. Perfect. Thank you so much. Thank you so much. Any questions? Now you can put it in the chat or Q&A section. I'll be able to take all of them. I'm all yours still. Okay, almost 2.5 hours. Thank you. I appreciate your patience and time. So I'll give enough time for your questions as well. Okay. So
Before we proceed to answer your questions, I would like to request the attendees to please fill in the poll about feedback, as it helps us to conduct more such sessions.
so you're still there. I thought you slept.
No, sir.
Okay, good. So we have very few people for the feedback. The last time I took it, there were more than 120 attendees, but I finished within time. That was a smaller topic, I guess. So attendees also have a lot of patience. We should appreciate them. So can we offer them some discounts?
Yes,
Okay,
sir.
no worries, no worries. Okay, so let me just go through the Q&A in the meantime. Okay, P less than 0.5 means that whatever claim. So okay. So out of all the several questions, mostly I have answered them during the session itself. One question I got from Ashwini is when is ANOVA used? ANOVA is analysis of variance. Now, just now we were discussing a case of 2 sample means. Now, what if I want to compare multiple sample means? Okay, a simple example. Let's say you have the sales figures with 0% discount, and then next week you ran a campaign with 10% discount. You will get another set of sales numbers. Then another week you ran the campaign with 20% discount. You'll get another sales numbers. And another week you ran the same sales campaign with 30% discount. So now you have got 4 sales figures. You have got 4 means. Now you want to figure out if there is a significant difference between these sample means. That is analysis of variance. Okay. So due to some intervention multiple times, if it is single time, then that can be tested with paired sample t-test. So many a times people, try to justify that ANOVA is nothing but repeated 2 sample test. Statistically, actually they are correct, but that is huge inconvenient, because then you have to compare sample 1 and 2, then sample 2, 3, then sample 3, 4, and also you have to compare 1, 4, and then 2, 4, and so on. So you would have to run repeated 2 sample tests. So instead of doing that, ANOVA will do that job in one go. So you wanted to find out whether this difference in the sales numbers is statistically significant. That is where the ANOVA is used. Jupyter Notebooks, what I'm going to do is once this video is uploaded in the YouTube, okay, just watch out for that channel. Within that comment itself, I'll add a link to download the notebooks. Okay, don't worry, you don't have to upload it, download it right now. Okay, I think I cannot upload it right now because of the permission settings. So don't worry, I'll give you a link to download this particular notebook. Okay, and that my handwriting as well if you want. This also I'll convert it into a PDF, and I'll share both, not just the notes but also the notebook both in the comment section. Okay, that is what I have done for my previous data sessions also. So in that recording part, in the comment, the first pinned comment, you will get the Jupyter Notebook. Promise. Okay, thank you.
Thanks a lot, Prashant sir. On behalf of Analytics Vidya, I would like to thank you for your time and for delivering such a wonderful session. I'm sure our audience found it insightful, and hopefully we can conduct more such session with you in the future. So LinkedIn profile of Prashant sir is in the chat box. I hope you guys have filled in the feedback poll. If not, I request you to please fill in the poll about feedback, as it helps us to conduct more such sessions. If you wish to conduct a webinar or are facing difficulty in registering or connect with us, so you can go at editor@analyticsvidya.com. The recording of the session will be available within 2 days on our YouTube channel. The link is in the chat box. We will be back with another session of the data tomorrow. The link is in the chat box. Till then, bye bye and keep learning. Thank you so much, Prashant sir.
Thank you, everyone. Thank you. Thank you.